Welcome everybody. This is 12.5 partial fraction decomposition, where fraction nightmares do come true, because we're going to take a fraction, a rational expression, and break it into what its original pieces were. That's what we're going to do here. That's why it's called partial fraction decomposition. And there are 4 cases to it. So let's get into the cases. We'll go over case 1. Case 1 says to decompose the rational expression P over Q, where Q is your denominator, has non-repeated linear factors. What's it mean to be linear? I guess we can go over some definition as well. What's it mean to be linear? Linear means that you could have a line, right? But we want to talk more about powers here. There are linears, quadratics, cubics, quartics. So if quadratic is a power of 2 and cubic is a power of 3, then linear must be the power of 1. That's it, right? To be linear. So if you have a linear factor that's non-repeated, you have factors to the power of 1, right? So to be linear means you have something such as x, or x minus 1, or x plus 1, and etc., 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 right? Those are linear factors. Okay. So when Q, the denominator, has only non-repeated linear factors, the rational expression has this form. So the fraction that we're given will have this form. P, whatever the polynomial is on top, over Q, the denominator with the non-repeated linear factors. And of course, I'll write in an example for you. Let's say I have just x over x plus 1, x minus 1. And what we see here is that the denominator is made of 2 linear factors that are not repeated. And when we say repeated, we mean, do we have the same thing? And that answer is no. So if you have something of this form, and yes, the denominator could have like 10, 20 unrepeated factors, which means as long as it has non-repeated factors, then the breakdown will be below. If this is the case for this type of partial fraction, then the breakdown, the decomposition, is going to be seen as A over the first linear factor plus B over the second linear factor plus C over the third, D over the fourth, Z over the 24th, right? 24 letters in the alphabet, or 26? I don't know. You get it. I think 26, right? Okay. So once again, what that composition would look like, using the example from above, if we were to break this down by case 1, then x over x plus 1 over x minus 1 would look like A over the first linear factor plus B over the second linear factor. And if there are more linear factors, we would keep going. C over the next one, D over the next one. That's how you would break it down. Okay. So that's how that would break down. That's case 1 for non-repeated. Okay. Case 2, very similar to case 1. Now the denominator Q has repeated linear factors, meaning you have the same linear factor repeated n amount of times. So if Q has a repeated linear factor, and of course, let me just do examples for all of these so we know what we're talking about. A repeated linear factor would mean I have x minus 1 times x minus 1, or x minus 1 squared, right? x minus 1 squared, x minus 1 cubed, x minus 1 to the 5th, to the 20th. As long as that factor is constantly repeated, it is a repeated linear factor. Okay, and then it says if q has the form of a repeated linear factor, x minus a to the nth, where n is greater than or equal to, meaning the exponent is 2 or greater, then the rational expression has the form p over x minus a to the n. Once again, let's just go with my example. Let's say we have p over x minus 1, I'll say cubed. So this means x minus 1 is repeated 3 times. All right. And then, let's see. So if it has this form, then the partial fraction decomposition, the breakdown is going to be right here. A over the first, what could I say? A over the first repeated factor, B over the second repeated factor, C over the third repeated factor, and depending on the power, that's how far you will extend it. So that's why it says Z to the x minus a over n. So if it's x minus 1 to the 3rd, I should have 3 breakdowns. If it's x minus 1 to the 5th, I should have 5 breakdowns. If it's x minus 1 to the 100th, I should have 100 breakdowns. And then when you break it down that much, you actually will have a mental breakdown. Okay? All right. So what this means is that if we decompose this function this way, this would be, I'll just keep it as p. P over x minus 1 cubed would become a over x minus 1 plus b over x minus 1 squared plus c over x minus 1 cubed. And whatever the power of the repeated factor is where you will stop. So the power, essentially the power determines how many fractions you will have, which is pretty cool. So once again, x minus 1 to the 3rd means we'll have 3 fractions. 1, 2, 3. So the power depends on how many fractions you will have. All right, that is case 2. Now let's get into case 3. Now the denominator q has a non-repeated, irreducible quadratic factor. All right, quadratic means to the power of 2. Good. So, and being irreducible means you cannot factor it. And being non-repeated means you can't repeat it. So what does a NIQF, or no, NRIQF, non-repeated irreducible quadratic factor, NRFB, never removed from box? It's hard. All right, had to throw it in there. Okay, so putting these together, well, that's too big. A not, stop it. There we go. A non-repeated irreducible quadratic factor means I would have something such as x squared plus 1, which is not factorable, or x squared plus x plus 1, which is not factorable as well, and it's not repeated, right? Remember, repeated would mean if this was in parentheses and was raised to the 2nd, we would have 2 of them, but we're only dealing with non-repeated. So you'd have something of that form where you cannot factor it, like let's say 2x plus 4. Cannot factor, and another non-repeated, irreducible quadratic factor. All right. So if the denominator q has a non-repeated irreducible quadratic factor, the rational expression has the form p over ax squared plus bx plus c, then the partial fraction decomposition is ax plus b over the irreducible quadratic factor, where a and b are to be determined. Okay. Like I said, we've been doing examples, so let's just I'll just keep it p, just to keep it simple, and I'll just say x squared plus x plus 1, where you cannot factor the denominator. So now you have an irreducible quadratic factor in your denominator, which means we now write the breakdown as, and I'll just put this back, x squared plus x plus 1, and this would become ax plus b over x squared plus x plus 1. That's it. And then we solve for a and b when we get there. Once again, we are just going over the cases and what they mean right now. How the breakdowns actually look. All right. Last case, case 4, which is just like case 3. This says that the denominator now has a repeated irreducible quadratic factor, an RIQF, which means that you now have a repeated irreducible quadratic factor. And that would look like x squared plus 1 squared, or x squared plus x plus 1 to the third, or x squared plus x plus 4 to the fifth, 6, 7, 100. This means it is being repeated, right? So let's say we have a denominator of q that looks like this, and we have the form, where can I write this? Now there's no more room, right? So again, just keep it simple. The form would be p over, I'll just say x squared plus 1 squared. We'll keep it simple. This means that the breakdown would become ax plus b over the first term of the repeated factor, and then cx plus d over the next term of the repeated factor, all the way till you get to that power. Remember, the power tells us how many fractions we will have. So if we put that into form, then the way I wrote my fraction over there, I would get ax plus b over x squared plus 1 plus cx plus d over x squared plus 1 squared. There you go. So once again, how do you know how to break it down? The power tells you how many fractions you need to break it down into. If that was to the power of 5, we would have 5 more. Or, well, we would have 5 total. You get it. Okay. Whew. Those are the cases. And that's how you break it down. So now let's start our examples and figure out what cases to use. And yes, cases can be combined. You can have a case 1 and a case 3. You can have a case 1 and a case 2. You can have a case 1 and a case 4. You can have a case 1, 2, 3, 4. You can use all cases together. Madness, I know. All right. Okay, so this says, write the partial fraction decomposition of x squared minus 5x plus 6. So our very first step is, can we factor the denominator? That's our first step always. If you can factor the denominator, let's go ahead and factor the denominator. All right. How much can I zoom in here? All right. Because we're going to need the room. So A is to factor. And looking back, x over x squared minus 5x plus 6 can definitely factor to x, what do we have? Minus minus, so x minus 3, x minus 2. X squared, negative 2, negative 3, negative 5, negative 3, negative 2, positive 6. Okay, step 1 is done. It has been factored. Step B, determine the cases. And to determine your cases, we look at the denominator. Does the denominator contain non-repeated factors? If so, label them. Look at our denominator. Are these linear factors? Yes. X minus 3 is to the power of 1. X minus 2 is to the power of 1. These are repeated factors. These are linear factors, and they are not repeated. So, knowing that, so B, this is going to be a case 1. Because we have non-repeated linear factors. Non-repeated linear factors of x minus 3 and x minus 2. There you go. That's all we do in step B, is we try to find out what case is this. Knowing the case is important to knowing the breakdown. And since we know the breakdown, well, since we know the case, now we know how to break down. So C is to decompose the rational expression. So let's just take a quick trip back up to the top. If it's case 1, then the breakdown, which is down here, is going to be A over the first linear factor plus B over the next linear factor. So this is how case 1 works. So C is to decompose. All right. Like I said, we're going to need a lot of room. Decompose. All right, so here's how it starts. We start with the factored version of our fraction. X over x minus 3 times x minus 2. And set it equal to its decomposition, which is going to be A over the first linear term, x minus 3, plus B over the second linear term. There's your breakdown. That is it. That's using the cases. No, we're not done. We have a long way to go. But we have just finished C. Now D, to help find A and B, because our job now is to solve for A and B, we must clear fractions on both sides of the equation. So that's D. Clear fractions, which means in order to clear fractions, you need to multiply by a common denominator. Well, secret, secret, hint, hint, wink, wink. Your common denominator is always the denominator on the left side. Always, always, always. That's always your common denominator. That makes life easy. So what we're going to do is take the common denominator of x minus 3 times x minus 2 and multiply it to both sides of the equation. There you go. Multiply both sides by the common denominator. And now distributing madness. This x minus 3 times x minus 2 distributes in there. And guess what's going to happen? These x minus 3 and x minus 2s and these x minus 3s, x minus 2s will cancel. So I'm going to zoom in again. Like I said, we need the room for this one. So this means that the left side becomes just x. Now on the right side, when you distribute this with this first term, the only thing that's going to cancel are the x minus 3s. When you distribute this with that, the only thing that cancels is x minus 3. So what we should be left with is a times x minus 2. And then for the next distribution, this one times this one. Now when you distribute it again, the only terms that cancel are going to be the x minus 2s, which means we should be left with b times x minus 3. And look at that. We have cleared the fractions out. All right. So the next step is to distribute everything. So this is still going to be step D. We'll get to step E in a second. So let's distribute everything and put like terms together. Bx minus 2a plus bx minus 3b. Watch your math, because this is a long process and you do not want to mess up one number. Do not do it. Okay. And then what I'm going to do is on the right side, I'm combining like terms, like variables. So okay. So the x's are with each other and the constants are with each other. So let's just put some definition on some things. These are my variable terms. And these are my constant terms. Okay, and the reason they're constants is because they don't have a variable of x attached to them, right? So just putting some definitions, because we're going to get to equating coefficients, which can be really, really confusing, okay? All right. So the next step is, what I'm going to do is factor out the x on the right side, just from the a and b. All right. So that's going to end step D. Now, step E is to equate coefficients of like powers of x. What does all that mean? I'll show you right now. Let's see. I'll just say equate. Save room. Okay, before I bring that back in, I'm going to show you what it means to equate coefficients, which means when you equate, you find something similar on the left side and something similar on the right side of the equation, and you equate them. You set their coefficients equal to each other. So this is just going to be a quick example I write down. Let's say that my left side is, I'll say my left side is 2x squared plus 3x plus 1. That's my left side. Now let's say my right side is x squared times, I'll just say a plus b, and x times a minus b. And then let's say I have plus, I'll just keep this 2a plus 3b. So once again, you see that x squared and x are considered my variable terms, and 2a and 3b are considered my constant terms. Now to equate, you look at the left side of the equation and the right side of the equation and see what variables they have in common. So this means that I see an x squared here, and I see an x squared there. So when you equate, you only equate coefficients. So here, the coefficient of 2x squared is 2. The coefficient of x squared times a plus b is a plus b. That's it. That's called equating. Okay, and then let's try it again. We have an x here, a 3x on the left side. Look on the right side. Do you have an x term? There it is. And equate again. So, and it's only coefficients. So you'll have 3 equal to the coefficient of this x term, which is a minus b. Once again, that's done. And then, last part, you have the constant. A constant is a number without a variable. So we have the constant of 1 on the left, and we look for constants on the right. All right, perfect. There is a constant of 1 on the left, and we set it equal to the only constants on the right, 2a plus 3b. And that's it. That is the equating process. That's it. You equate coefficients of x terms with like powers. That's how you do it. And then after you do it, you of course solve for a and b by possibly using a system of equations. All the algebra comes back. It's fun-packed. Okay, so now remember, this was just an example. So now we actually have to go back to our purple writing above and finish it and equate coefficients. All right, zoom in as much as I can. There we go. So we are equating, and I have x equals, actually we're in orange, right? Okay. I have rewrote everything, and now we equate like terms on the left side and right side. We equate the coefficients, right? Okay. We have an x here, we have an x here. Well, what is the coefficient of this x? What is the number in front of that? That is a 1. Equal to the coefficient of this x, which is a plus b. I guess I could write it as a plus b plus a plus b times x to make it look more like the coefficient. Okay. Which means that 1 gets set equal to a plus b. And then we are left with constants. Well, do you see a constant on the left side? We do not. So since you do not see a constant on the left side, guess what number represents nothing? If you do not see a constant, then the constant on the left side is going to be represented by 0, right? Because I could write this as x plus 0 equals. So this means, easy enough, we take 0 and set it equal to the constants on the right side. There's our equations. And now we must solve for a and b using substitution properties or maybe even a system of equations. So E is done. Now we're on to F. Solve the system of equations to find A and B. And the way to solve a system is by substitution or elimination. So here, let's do this. So here's F. It's just going to be called solve. So what I'm going to do is take my equation. I'm going to rewrite it the other way though. A plus B equal to 1 and put it over my other equation. Negative 2a minus 3b equal to 0 and put it as a system of equations. Algebra coming to haunt you. Back from the past, right? Okay. Well, to solve the system the fastest, we're just going to use elimination method, which means if you use elimination method, you get to multiply either the first or second equation, or maybe both, by a number that will help us get rid of a variable. So I say, when I add these two equations together, I want to eliminate A. So if I add these equations together, in order to eliminate A, this A needs to become 2A. And in order to do that, all I have to do is multiply this equation by 2. And I'll write the new equation below. I'll use that color. So now, once I multiply it by 2, I get 2a plus 2b equal to 2. The second equation comes down. We have not added them yet. Negative 2a minus 3b equals 0. And now, to solve this system, we add the equations together, right? You add them, and 2a plus negative 2a, gone. 2b plus negative 3b is negative b equal to 2. Therefore, b equals negative 2. And since you have b, you can now solve for a. So we're going to say, since you have b equals negative 2, we're going to say find a. And I'm going to use the first equation given. A plus b equals 1. plug in -2 for B, and A plus -2 equals 1, which means A minus 2 equals 1. Add the 2 over, and A equals 3. Woo, right? Step F is done. Step G, since we know A and B, you can now finish the P of D, the partial fraction composition, which means zoom in right here. All I want is this part for the answer. Plug in A, plug in B, and we're done. So I'll keep that up there. Let's see. Hey, and we had room left. So I'll say this is G. The final answer is A, which is 3, is going to be 3 over x minus 3 plus B, which is -2 over x minus 2. That is your final answer. Oof. Fun stuff, right? I don't know how long this video is going to be. Probably have to break it into 2 parts. But that is the method you will use. Now, is there another way to solve these? Yes, and it's actually a lot faster. But sometimes it doesn't work. So it is a shortcut, but sometimes if you use the shortcut, it will have to be combined with the long way as well to make work easier. So let's go over the shortcut, which I like to call the X games. So right here, I'll block this off with some, let's see, is that a pencil? Delete that. Add me another pen in there with some foo-foo glitter. All right. So here's where we start. The X games. Okay. So to start the X games, you do have to still do A, B, C, and D. But for part D, you will stop right here. So this is where the X games begin. The X games begin right here. So let me write that down. Here's where the X games begin. X equals A times x minus 2 plus B times x minus 3. Okay. So we start the X games here. And the reason it's called X games is because we say, what value of X could we choose? What value of X could we choose that would eliminate A? So what could I plug in for this X that could eliminate my A and help me solve for B? Or you say it the other way around. How could I eliminate B and solve for A? But let's go off what I said in the beginning. So choose a value for X that will eliminate A and help us to solve for B. And the only way to do that is to choose, oops, I'm everywhere. We will say, let X equal 2, which means you take this 2 and you plug it in for all the X's you see. So starting with the left side, we'll have 2 equals A times 2 minus 2 plus B times 2 minus 3, and clean it up. 2 equals A times 0 plus b times -1. And then 2 equals just -b. And guess what? You get b equals -2. Oh my goodness, right? Look at that. We just found -2 in less than all the amount of time we took to find this b is -2. X Games is a glorious thing, isn't it? Look how much time we just saved. We didn't even have to do a system of equations. Oh, all right. Well, let's keep going. Because now we have to find a. So, once again, we ask the question for the X Games, and we say, now, what value of X could we pick that would eliminate B to help us solve for A? Whoops, we'll go back. All right. Erase that. And if you guessed it, yes, we let X equal 3. And once again, plug it in for all the X's above. 3 equals A times 3 minus 2 plus B times 3 minus 3. Which then gives us 3 equal to A times 1 plus B times 0, which means we just get 3 equals A. And guess what? We're done. No system of equations needed. You now know B, you now know A, no equating, no confusing equating either. And guess what? You take these two answers and we are done. X Games. Use it if you want, or go the long way. Probably to sum up this video, I'm going to X Games everything, if I can. Well, that's it. Another two methods to solve this problem. All right. Yeah, it's good. Okay. All right, so from here on out, I'm probably just going to blaze through these. So hold on to your hats. All right. I can say Samuel Jackson's line from Jurassic Park, right? Hold on to your butts. Okay. So here we go. Factor this bad boy. X plus 2 over x cubed minus 2x squared plus x. All right. Okay. Factor. And we get x squared over x times x squared minus 2x plus 1. Which then gives me x squared over x times x minus 1 squared. Boom. There's A. B. Here's our cases. All right. So we see that we have a non-repeated linear factor of x. So that's going to be a case 1. You have a non-repeated linear factor of x. And then we have x minus 1 squared, which means that is a case 2. We have a repeated linear factor of x minus 1 squared. So this will be a case 1 and case 2 combined. So we have that, which means we can move to the breakdown. All right. Start with the fraction, the factored one, and decompose. Well, do case 1 first. If you want to do case 2 first, you can. You can decompose them however you want. Just make sure to follow the rules. I like to go in order, so I'm doing case 1 first, which means I'll get a over x. There it is. Case 1 is done. Now we apply case 2. b over the first factor, or first term of x minus 1. I guess factor. And then plus c over the last repeated factor of x minus 1. Remember, that was x minus 1 squared, which means I should have 2 fractions right there. Okay. D, clear everything up. D is to clear. And remember, the trick is your common denominator is always the denominator on the left side. So there it is, and distribute, distribute, distribute. I'll be left with x squared on the left. On the right side, I'll have there it is. So D is done, and now I'm gonna play X games. Like I said, I don't want this video to be 2 hours. So I'm gonna call that, what are we on? That was D, so this would be E. And now let's say I want to solve for A. So I'm going to solve for A, which means I need to choose the number for these x's to get rid of B and C, and that number is going to be 0. So I'll get 0 squared equal to A times 0 minus 1 squared plus B times 0 times 0 minus 1 plus C times 0. Which means I'll get 0 equals A times negative 1 squared. Everything over here just becomes 0. And then I get that. I get 0 equals A. All right. There we go. Ah. Ha. See? I was like, that's not right. Well, I'm not going to re-record this, right? So I know what I have to do. My bad. So, not x squared. X plus 2. I was like, A can't be 0, or we won't get our fraction. See how important it is not to make a mistake? It's a good thing that didn't affect the denominators. You're probably yelling at me through the screen, it's x plus 2. This is what happens when you do turbo math. So watch everything. There we go. That makes more sense now. Okay, now we have A for 2. We fixed our little mistake, or I fixed it. I'll blame this on the viewer since you can't say anything. Okay, and then we solve for A, so now let's solve for, let's solve for C. Yeah. So we have to solve for C, so we kind of have to be smart about what we pick, because if I wanted to solve for B, I would have to eliminate C, and the only way to eliminate C is to plug in 0. But if I plug in 0, this becomes 0, and I won't get my answer for B. So you have to be smart when you're doing X games as well. So we are going to actually solve for C, and to solve for C, I'm going to have to eliminate B by choosing 1 for X. Okay, so let's do that. So let X equal 1. And then you get 1 plus 2 equal to A times 1 minus 1 squared plus B times 1 minus 1 plus C times 1. Okay. Put it all together. And on the left side, you get 3. Over here, this becomes 0, that becomes 0. And we are just left with C. All right, we now have A, we now have C. Now all we have to do is solve for B. Now here's the fun part. We don't have to do too much thinking because now we can choose any number we want to solve for B, except for the numbers we have chosen already. Do not pick 0, do not pick 1, pick another number. And I would suggest picking small numbers, right? I said you can let X be anything. If you want to plug in 200, 2000, go ahead. We're going to get the same answer as if we plugged in 2 or -1. So for this one, I want to keep things simple. So let's go ahead and plug in 2. Let's just say 2. So we're going to say so you'll get 2 plus 2 equal to A times 2 minus 1 squared plus B times 2 minus 1 plus C times 2. Clean up. 4 equals A times 1 squared plus 2B times 1, which is there, and then plus 2C. All right, and the great part about this, I'm running out of room, is that we already know the values for A and we know the values for C. So plug them in. 2 is going to go in for A. 3 is going to go in for C. So we're going to get 4 equals 2 plus 2B plus 2 times c, which is 3, which means we'll get 4 equals 2 plus 2 times 3, so that's 6. So you're going to get 8 plus 2b. And then, let's see. Oh, I could have moved all that to the left. Maybe I still can. One moment. Hey, look at that. Magic. All right. And then move that 8 over, and you'll get -4 equals 2b. Therefore, if you divide by 2, b is -2. And now we're ready for our final answer, which is we move on to G, right? Because we skipped F, we didn't have to do a system of equations, which means we go straight to G, our solution. So A over X, so 2 over X plus B, -2 over X minus 1 plus C, and there it is. There's our answer by X Games. If you want to see the long route, well, you can ask during class, and it'll probably take up a whole class, but that's okay. All right, keep moving, keep moving, keep moving. We got 1, 2 left. Okay, perfect. All right, 3x minus 5 over x cubed minus 1. Let me make sure I write it down first properly, right? And use all the room I can. Okay. And then factor. So zoom in for that. So down below is a difference of cubes, right? So this is a which factors to a minus b times a squared plus ab plus b squared. Just remember those formulas, right? Okay. And then, yes. All right. So now factor. There it is. Done. We cannot factor x squared plus x plus 1, so this is our irreducible quadratic factor. Hoorah, lots of talking, right? Which means B come on, laptop, love me. Cases, well, look at the first term, x minus 1 is a linear factor that is non-repeated. So that is case 1. And then look at the second factor, x squared plus x plus 1. That is a non-repeated quadratic factor. Non-repeated irreducible quadratic factor, which is a case 3. Non-repeated irreducible quadratic factor of so we have a case 1 and case 3. So let's get ready for the breakdown. decompose. All right. So start with the factored one, the correctly factored and correctly written 3x minus 5 over that. Okay. All right. So again, I like to go in order by cases. So first is a case 1 breakdown of the non-repeated linear factor, which is just a over x minus 1, plus a case 3 breakdown. So now we go, of course, the next letters in the alphabet, and the case 3 breakdown would be bx plus c over the irreducible quadratic factor. And there's your decomposition. D. Clear. All right, once again, common denominators right there. All right, multiply by the common denominator and clear. Write everything down perfectly, right? A over x minus 1. Okay, then that cancel, and then you have, don't forget to put these in parentheses. All right. And for this one, I am not going to do X games. You can do it to get rid of B and C. Yeah, you could do it. But I'll switch off fun and on. So let's do this the long way. Okay. So very important to watch everything and see how mistakes can ruin this whole thing. So write everything down correctly. Very easy to lose your place and lose focus. Ax squared, axa, bx squared, negative bx, cx minus c. Okay. ax squared plus bx, ax minus bx plus cx, and then okay. I just marked them off to make sure I had them in order, and I'm not missing anything. All right, so that's done. So now we can try the equate again. And looking at this, there's an x squared here, but there's no x squared there. So once again, what equates to nothing is 0. So that means for the first ones, I mean, I could write this as 0x squared, right? Which means that you have a 0 on the left side and you have the coefficient on the right side. So this means that 0 is going to be equal to a plus b. Okay. And then I have 3x here and an x here, which means 3 is going to equal a minus b plus c. And then I have my constant of -5 and my constant of a minus c. So this means -5 will equal a minus c. All right. Now we have everything equated. And now we have to figure how to solve for a, how to solve for b, and how to solve for c. So here's f is going to be our system. So we do have to do a lot of rearranging right now. So you have to think about what do we need to arrange to put in terms, because right now that c is probably throwing everything off, right? So what I'm going to do here is I'm going to solve the third equation in terms of c. So that's what I'm going to do first. So I'm going to say, if I move that a over, I have -5 minus a equals -c. And then I'll divide everything by -1, and I'll get 5 plus a equal to c. Okay, so that's rearranged, and now what I'm going to do with that is plug this into the second equation, which means we'll get 3 equals a minus b plus the new c value of 5 plus a, which means we'll get 3 equals, and this a and that a make 2a, and then you'll have minus b plus 5. All right. Then what I'm going to do next is move this 5 to the 3, and we get an equation, another equation in terms of a and b. So I move that 5 over, I'll get -2 equals 2a minus b. And then what I'm going to do next is set up a system. I'm going to put this equation with that equation. All right. So what we're going to have is and I'm going to rearrange it again. A plus b equal to 0 over and create another system. Which means we'll do it by elimination method. And what's great is that if I add these together already, b is going to be eliminated. So if I add these together, b is gone, and I get (3a equals -2), and therefore a is -2/3, which means all we have to do now is find b and c. So let's say and to find b, I'll use this equation again. 0 equals a plus b. Where b is going to equal -a. And look at that. We know a already. It's to the left. And we're going to get b is +2/3. And then last is find c, where looking right above, we made an equation for c already. That is c equals 5 plus a. Plug in a. And clean it up. And 5 minus 2/3, 5 times 3 is 15. 15 minus 2 is 13. So c is 13/3. Woo! Fun stuff, guys. All right. Okay. And last is writing the equation. Or writing the answer. So G, A, B, C, D, E, F, G. Here's our answer. -2/3 over x minus 1 plus b, which is 2/3 x plus c, which is 13/3 over x squared plus x plus 1. Aren't these just fun? All right. Yeehaw. Last one. All right. X cubed plus x squared over x squared plus 4 squared. All right. A, factor the denominator. There we go. One more. x cubed plus x squared over x squared plus 4 squared. Okay, well, this cannot factor because it's a sum of squares, so our job is done. That's easy. Can't factor. Okay, which means B is your cases. What you see here is an irreducible quadratic that is repeated, right? An irreducible quadratic. So this is actually case 4. We have a repeated irreducible quadratic factor of okay, which means C, decompose, you'll get x cubed plus x squared over x squared plus 4 squared equal to, and this is a case 4 breakdown. So the way this will start is ax plus b over the first term of the repeated factor plus cx plus d over the last term of the repeated factor. All right. You're just going to double check to make sure I wrote everything down correctly. Remember, breathe. Okay. X cubed plus x squared, good. Ax plus b over x squared plus 4 over x squared plus 4 squared, good. Okay, so remember, once again, the power tells you how many fractions you should have. All right. And now the clear part. Common denominator is always on the left side. All right, clear out fractions, distribute, and you'll have and remember, parentheses around everything. So and once again, I'll do this one the long way because X games could work, but it will only let us solve for D and nothing else. So we don't want to do that. X cubed for a x we get squared 4b cxt. Okay. Put like terms together. And these stay the same. Okay. That is the end of step D. And then step F, E. Equate. Okay. Whew. You have 1x cubed here. You have an ax cubed there. So we have our first answer for A. Remember, you equate coefficients. So A is going to be 1. Hey, easy, right? And then you've got an x squared here and a bx squared there. Equate the coefficients and b equals 1. Oh man, looking good. We have an x here, but no x by itself over there. So once again, what represents nothing? You would put a 0. So 0 would equal 4a plus c. And last one, constants over here. No constant shown over there. And what number represents nothing again? 0. All right. So all we have left to do is solve for C and D, which looks really simple from here. So A is 1, B is 1. So just find C by plugging in 1 for A on that equation, right? So you'll get 0 equals 4 times 1 plus C, and therefore C is -4. And then on this one, solve for D by plugging in 1 for B, and you'll get 0 equals 4 times 1 plus D, and D equals -4. Done. That one was nice. And then G, we want the answer. So ax plus b, so you have x plus 1 over x squared plus 4 plus cx plus d, -4x minus 4 over x squared plus 4 squared. There it is. Whew. That is partial fraction decomposition, which brings everything algebra back that you know: substitutions, elimination, system of equations, clearing out fractions, distributing, combining like terms. It is so algebra based, it's not even funny. The only thing you shouldn't do is what I did: mess up rewriting it. Ugh. I mean, I think the algebra was perfect. It's just that we had a couple of rewriting issues that were easy to fix. Let's just hope you catch them in the beginning. Make sure to write everything down properly. Like that one was x plus 2, and I wrote x squared. So just catch your mistakes like that. Okay, that's PFDs. Till next time.